Okay, I think we're good to go. So last week, we got started on the quantum mechanics and worked our way through to what's called the Liouville von Neumann equation, which is shown maybe here. Pointer. You can see it. Sorry about the green line. None of us know where it came from. And so it relates the density operator to the time dependence of the density operator to the commutator between the Hamiltonian and the density operator, as opposed to the Schrodinger equation, that's the time dependence of the wave function. And again, the reason for doing this was that we have a Boltzmann equilibrium distribution of states, not a pure quantum mechanical state. And you could say, when we want the average expectation value of some measurable quantity, that we could, of course, do the calculation once for one state, and then again for another state, and build up the Boltzmann equilibrium that way, where each state we get the expectation value is the average over a large number of identically prepared states in that particular Boltzmann level. But that turns out to be very inefficient. So by using the density operator, we've done the averaging once over the Boltzmann distribution, and we don't have to keep doing it over and over again. I mean, it could be if you were doing a computer simulation, maybe you do it brute force. We don't need to do that. And that's really the advantage of going to this density operator representation. And then, just like there was the solution to the Schrodinger equation, if the Hamiltonian is time independent, we have the solution for the density operator when the Hamiltonian is time independent. And that's given by this kind of sandwich where we have the exponential of minus I ht acting on the density operator times 0, and then e to the plus I ht acting on the density operator. If we have a piecewise series of time-independent Hamiltonians, then we would just repeat this over and over again. We propagate from, say, time 0 to time t1, and then time t1 would go in the middle. We have a new Hamiltonian or a new time interval. And we can just do this over and over again as long as we have a piecewise series of time-independent Hamiltonians. So the problem is how to get a time-independent Hamiltonian. And our goal then, at least for a while, is going to be to find a transformation that makes the Hamiltonian independent of time. And for solution NMR, that's going to be the rotating frame transformation. In solid state NMR, this is going to be more complicated because one needs transformations from frames of the Hamiltonian, the principal axis frames of the Hamiltonian, the molecular frames to crystal-like frames to rotor frames to lab frames. But in solution, it's very simple. While we'll present this in abstract fashion, it's really just the rotating frame transformation is enough. So the frame transformation is also going to be represented by this kind of three-step or sandwich here between the unitary matrix U, the density operator in the original frame, the unitary matrix U minus 1 will give the density operator in the new frame. As I said, a unitary operator or a unitary matrix has the property that the adjoint is equal to the inverse of the operator. That's distinct from a Hermitian operator or Hermitian matrix, where the adjoint is equal to the operator. And you can easily see back here that this operator, the exponential of minus I ht, is unitary because the adjoint I get just by changing the I to minus I, because the Hamiltonian is always Hermitian. So its adjoint is itself. And clearly, e to the minus I ht times e to the I ht is going to be e to the 0, which is 1. So these are the adjoint of this is its inverse. So this is unitary operation because the Hamiltonian in quantum mechanics is Hermitian. So that's one example of this kind of procedure. But then we can ask what the time dependence of the new operator is in the new frame just by applying the rules of calculus. So if I want to know what the time derivative of the density operator is in the new frame, this little r here is to indicate that I'm thinking in solution NMR about the rotating frame, but it's just some arbitrary new frame. So that's the time differential of u sigma u minus 1. And then I just have to apply the chain rule of calculus, and I have the sum of three derivatives. The derivative with respect to sigma, the derivative with respect to u, the derivative with respect to u minus 1. Well, the derivative with respect to of sigma with respect to t, I already know. That's just the commutator with respect to h, so I can plug that in. And then I can play a game that gets played all over again in quantum mechanics. Is here I have the derivative of u with respect to t times sigma times u minus 1. And I play the game of inserting the identity operation. I can always insert a 1 anywhere I want. And u minus 1 times u is the identity operator. I've inserted that here because I know what u sigma u minus 1 is. That's just sigma r. And I do the same thing over here. I insert u minus 1 u, which is equal to 1. But then u sigma u minus 1 is sigma r. So I've ended up on this last line then replacing the u sigma u minus 1 with sigma r wherever I can. So, of course, I know the answer that I want. I know I should do this because I already know the answer. It's not so clear to you doing this the first time why I should do this. But I'm always trying to get the equation back to something that I recognize, just with new variables. So I'm left with this, and I want to try to figure out what u dt u minus 1 is relative to u du minus 1d. So, of course, their product is just the identity. The derivative of the identity is 0. And if I apply the chain rule, I have du times u minus 1 plus u times du minus 1 dt. That all has to be 0. So I have a relationship between these two derivatives from the previous equation. Here I have the derivative of u times u minus 1. Here I have the u times the derivative of u minus 1. I want to establish a relationship between them. And I do it by recognizing that their product is the identity, and then I can get a relationship between them. And so I plug that in. And I end up just following through to end up with this result, that now the time dependence, the density operator in the new frame is now still a commutator of the new density operator with an effective Hamiltonian that has this rather complicated form. And probably so here I've just called it an effective Hamiltonian. So I have the same form, the form of the equation is the same. I have this effective Hamiltonian that's given by a transformation of the Hamiltonian plus a correction for the time dependence of the transforming variable. You could think of this minus IU du minus 1 dt as a kind of fictitious Hamiltonian caused by the change in reference frame. And again, if you think back to the amusement park ride, where you're against the wall and the room is spinning in a circle, and then the floor drops away and you don't go anywhere, to you it looks like the Hamiltonian is zero. The Hamiltonian of gravity pulling you down is offset by a fictitious Hamiltonian, the centripetal force caused by the rotating room. And in that new frame, the rotating frame, the net force looks to be zero, so you just are pinned against the wall. So here, the same thing is happening. If U is time dependent, there's now some fictitious component of the Hamiltonian in the new frame. And our goal is to make use of that by having this new term cancel the time dependence of this term. And if we can cancel the time dependence, then in the new frame, the density operator is independent of time. We know how to solve the equation for a time-independent Hamiltonian. We can solve the equation, we have the density operator, and then we can transform back to the initial frame, and we're done. From now until we get to relaxation theory, we'll always be able to do this because all we need is the rotating frame transformation. When we get to relaxation, when we get to aspects of solid state NMR, we may not be able to find a transformation that gets to a time-independent Hamiltonian. But we'll try to get to a frame where the time dependence is as simple or small as possible, to where we then might be able to apply some approximations that are good enough for our needs. And if we can't, we're going to just have to go back to brute force computer calculations. Most of the time, there are transformations that will at least simplify the problem that we have to solve. So here's the result. If the Hamiltonian is independent of time in the new frame, we can solve for the time dependence of the Hamiltonian new frame, and then just undo the transformation U to get back to the original frame. So here we have the Hamiltonian in the original frame. We transform it to the new frame. We solve in the new frame using the effective Hamiltonian, and then we transform back to the original frame. And again, if we had piecewise Hamiltonians in each period of time, we would try to find a transformation U. We would do this and then use that for the next block of time where we may have a new transformation. I mean, this is so central to everything else that happens. Let me pause here and ask questions. Any questions online? I can't see the chat on my computer, so you have questions online, you have to unmute and speak.
So you get essentially the same form of the equation that you started with. And I think that's what you expect for a frame transformation. Because it's conservative and unitary and all that.
Well, only
But
if we
you have
pick
to-
the right frame transformation. So if U is unitary, this is always going to be true. In the
That's what I
new
said.
frame,
Yeah.
the effective Hamiltonian is the transformed Hamiltonian corrected by what I was calling the fictitious part, the part that came from the transformation. Now, if I'm successful, if I've chosen U wisely, then I hope that the effective Hamiltonian is independent of time. But that would only be true for a specific U, depending on what the Hamiltonian looks like. There's going to be perhaps only one U that will do the trick, or maybe there won't even be one. But certainly, if I choose U unwisely, this equation is still going to be true, but H won't be independent of time. And if it's not independent of time, I don't have this simple solution. I then have to do something else.
Are all unitary operators like basically rotations or reflections also unitary or?
And help.
I didn't hear the question.
The
Are all
question is,
unitary operators like basically rotations or are reflections also unitary?
They could be, so you change the chirality, but you preserve the size, but not every reflection is unitary.
Can you explain what's going on in the last equation?
Mhm. So if I solve for sigma of R, or in the transform frame, if I want to come back to the laboratory frame, I'm going to have to take my new sigma of R and actually there is a typo here. This should be a T here. To get back to the original frame, I'm going to have to pre-multiply here by U minus 1 and post-multiply by U. And then I'll be back in the original frame, assuming this was a T. So down here, we said
Oh, okay. That
U
makes sense.
sigma of T in the rotating frame was going to be e to the minus IH sigma R in at time 0, e to the IH of T. So I substituted here U sigma U minus 1, and then I pre-multiplied by U minus 1 and post-multiplied by U to get everything back. So I start in the original frame, I transform to the new frame here, solve in the new frame, and then transfer back to the original frame. Depending on the problem, I might not care about coming back to the original frame. Knowing the result in the transform frame might be enough for me.
So the superscript R is missing in the last equation, sigma R0, or is it just sigma 0?
This is sigma 0 because the U minus 1 transforms it to the R frame.
Okay.
So here I plugged in for sigma R0, I plugged in U sigma U minus 1. I'll fix this typo. for example, the spectrometer basically is working in the rotating frame. When you see the spectrum, it's as if the spectrometer is in the rotating frame. So unless we are talking about relaxation, once we switch into the rotating frame, we may not need to switch out again for analyzing pulse sequences. Other times we have to come back out of whatever transform frame we're in. What are we doing? I think we can skip that for the time being and come back to it. Now, of course, to make progress, we need to know what the Hamiltonians look like. So we need three things here. We need to know the starting density operator, the density operator at Boltzmann equilibrium. We need to know what the Hamiltonians look like in this new picture. And we need to know what our unitary transformations are. And to do that, we have to define what are called the spin operators and our different wave functions. And NMR is nice because as long as we talk about one or two spins, the dimensions of the matrices we have to deal with aren't that large. And we have to talk about a large number of spins, we're probably going to do a computer calculation anyhow. So to some extent, I'm just going to write these things down and say these are the right matrices for these operators. And of course, without doing too much mathematics, we could always say, well, if these are the right operators, when I get done with the calculation, I should be able to go to the NMR machine and do an experiment and see the answer and show that it works. That's the case. So here is what we'll call the IX operator, the IY operator, and the IZ operator for a single spin 1/2 particle, or 1H spin. And here are the representations of the eigenstates, and they're just column vectors. And the conjugate are the corresponding row vectors. And if you had taken a quantum mechanics class at some point, when spin angular momentum was talked about, you would have been told something like the IX operator acting on the alpha state gives back 1/2 of the beta state. But we, of course, can just work these out with these matrices by just doing matrix algebra. So, for example, here is IZ acting on the alpha state. IZ is 1/2 of the matrix 1, 0, 0, -1. Alpha is the column vector 1, 0. I do the math, and then I recognize the result is just 1/2 alpha. So IZ acting on alpha gives back 1/2 alpha. And that means that alpha is an eigenvector of the IZ operator. Because we got back to put in I alpha, we got back I alpha. 1/2 is the eigenvalue. And in this case, the eigenvalue is just the magnetic quantum number for alpha. And if we do the same thing for beta, we get IZ acting on beta, gives back minus a half beta. So beta is an eigenvector of the IZ operator, and the eigenvalue is minus a half, which again is just the magnetic quantum number for the beta state. On the other hand, IX acting on alpha, if you do the math, which I think is probably in the problem set, you don't get back I alpha again, you get back I beta. So alpha is not an eigenstate of the IX operator, although we could work out what the eigenstates are. Now, a key point, harking back to the first lecture, was that if we have some arbitrary wave function, we can represent it as a linear combination of a set of basis functions. And here we only have two basis functions. That's what makes life easy for NMR, alpha and beta. So any arbitrary column vector is a linear combination of these two with coefficients C alpha and C beta, which are numbers. They might be time-dependent numbers, they might be complex numbers, but they're numbers. And if we just do the arithmetic, right, this is kind of trivially simple. This vector is a column vector of two arbitrary numbers, and they can be written in this expansion. And if we did it the other way, to get the bra, we would take the complex conjugates, we would have the row vectors, and we just end up corresponding row vector. So for spin 1/2, since the wave functions are just column vectors with two entries, any vector with two entries can be represented as a linear combination of these two. And if we transform with, again, a unitary matrix, we just do the transformation here by multiplying by U, and U, this matrix, a representation that what would be called its matrix representation, in which a given element, U sub ij, would be given by this recipe, where we multiply on the right, on the left, by the bra I, and then on the left by the ket j. U acting on j is just j represented in the primed basis. So this also can be written as the projection I onto j prime. That way. What this means then, remember, is the expectation value was given by the bra times the Hermitian operator associated with some measurable times the ket. So if we do this in the transform frame and I plug in the inverse transformation going back to an original frame, and then plug in what the transform frame is, I quickly find that the expectation values don't depend on the frame. Well, that's a great simplification. Of course, the expectation value is something you're measuring in the lab. If I measure something in the lab that comes out of the NMR machine, you don't expect it to depend on my imagining whether I'm in the rotating frame or the lab frame. Something that's measurable should be a fixed quantity. It shouldn't depend on my mental manipulations. Well, that's a good thing. All right, so now how do we get to Hamiltonian? Well, we already went to our physics friends who told us that the energy is for a magnetic dipole in a magnetic field is minus mu dot B, where B is the magnetic field and U is the magnetic moment. And the recipe in quantum mechanics says that we go from the classical expression for energy to the quantum mechanical Hamiltonian by replacing everything with their corresponding operators. Now, mu, remember, was the angular momentum operators times gamma h bar. And we call that combination, we call it minus gamma B omega, and then decided to work in a system where h bar was equal to 1. So we're in frequency units. So if I just make those substitutions, I find that this Hamiltonian is just the Larmor frequencies adjusted for the chemical shift, which I glossed over. It was the end of the notes of the first lecture. You can look at that, and Ann will say more about it. But that's where dispersion comes from. And then just the different projections of the B field onto the 3 axes. And I've imagined in this case that my Z field is independent of time. That's just going to be B naught. But the X and Y fields might be time dependent because I imagine those are where I turn on the RF. So this Hamiltonian looks very similar to what I wrote down just for the block equations, except now I have these quantum mechanical operators. So these symbols are really 2 by 2 matrices. But as you'll see, we'll try to manipulate the symbols more than the matrices as we go forward. Yep.
Sorry, what's omega 1 again?
Omega 1 would just be the amplitude of the B field, B magnetic field, measured in angular units. So the amplitude of the B field, of course, is in Tesla or millitesla, but it appears multiplied by gamma and h bar. So I say I'm going to call that a frequency.
So we have the static magnetic field, we have the magnetic field from this RF.
So a very simple way, think of it, hopefully. Now I have to remember how to switch over to the blackboard. So this will be our first attempt doing that. Hopefully people on board can now, online can now see the board. So when I turn on the V1 field, is of course modulated sinusoidal. That's generated by the coil and the probe, and it has a frequency of omega RF, 500 megahertz, plus whatever I set the carrier frequency to. It has an amplitude that, of course, is measured in Tesla, but the effect on the spins depends on gamma B1, its amplitude. And also minus signs floating around, that's okay. I'm going to measure the amplitude not in Tesla, but in angular units. And the easiest way to think about that is if I turn on the V1 field on resonance, say along the x-axis, and I have magnetization on Z, I expect that that's going to rotate right, in the ZY plane. And after a certain amount of time, we'll come back by 360 degrees. So omega 1, well, 2 pi, let's stay in angular. So this frequency is the time it takes to go to 2 pi. So if I measure on the spectrometer a 360-degree pulse, then the amplitude of the B1 field measured as a rotation frequency is then the time to rotate by 2 pi divided by the time. So I'm thinking about the strength of the B1 field in the rotation that it induces of the magnetization. And if I turn up the amplifier, the time to do a rotation, a 360 rotation is going to be shorter, and I'm going to say omega 1 is larger.
And we can also say that the RF frequency is amplitude modulated, or E1 amplitude modulated with E1.
Well, the sinusoidal modulation, of course, amplitude modulates signal. But here, maybe I should say, I think of this right as the maximum. In this equation. But the important thing you have to keep track, it's confusing, is omega 1 is the amplitude of the RF field measured as by how fast it rotates the magnetization. So of course, if I turn on a certain amplitude pulse in the amplifier, omega 1, with the same power coming out of the amplifier, omega 1 is going to be different if I'm then applying it to the hydrogens versus, say, the nitrogens, because gamma is different. So the same power generates different amplitudes measured in frequency units depending on what nucleus we. And that's why if you go down and look on the spectrometers, the hydrogen amp is only putting out a few tens of watts, whereas the nitrogen amplifier is putting out a few hundred watts. And that's to get roughly comparable values of omega 1, even though gamma differs by a factor of 10. So to get comparable amplitudes measured in omega 1, we need 10 times the power, basically, for nitrogen. So sometimes to try to keep the difference clear between omega 1 and omega RF, I'll try to refer to omega 1 as the Rabi frequency after Isidore Rabi. And that's how the magnetization is rotated. Frequency that the magnetization is rotated by the pulse, as opposed to this frequency. And
I just wanted to add something, the power should be like gamma squared because the voltage or the C1 field should be like gamma, but the power is the square of that. But you don't really see that because the efficiency of the probe as you go up in frequency, it's harder and harder. So in reality, it is more like almost like linear and gamma. But if the photon frequencies worked perfectly, it would be an astonishing difference, I think, in the power to get to the same.
And this difference between power and omega one comes up actually, when you're actually calculating how many decibels of power it takes to have the pulse length, it ends up taking 6 dB rather than 3 dB, which is what you would expect. It's because of the squared relationship. Nothing else, we've been relatively successful in our first attempt to use the whiteboard.
The rest will be happening.
Let's see. As good as Zoom is, it doesn't make this so simple. Switching between. So our rotating frame transformation is a rotation around the z-axis. So I'm going to tell you at this point without proof that the unitary matrix associated with the rotation around the z-axis is the exponential I omega RF T times IZ. Later on, we'll prove that this is the case, but for right now, I'm just going to tell you that this equation represents a rotation around the z-axis with a frequency omega RF, which is the frequency of our B1 field. So then, if we do a frame transformation by this rotation, what is the effective Hamiltonian? And here was our equation. So we have to multiply this Hamiltonian by this unitary matrix, and we have to calculate this derivative. So here I've just plugged in. I have to multiply on one side of the operator by u and the other side of the operator by u minus 1. Omega naught and 1 minus sigma, these are just numbers, so they can come outside of the effect of the operation. Here I had to multiply Ix on one side by the transformation. Here's the Iy part, and then on the other side by minus. And then I have to calculate this minus IU du minus 1 dt. U minus 1 is e to the minus I omega RFT. If I do take the derivative with respect to time, I get minus I omega RF IZ times u minus 1 again. U times u minus 1 is the identity operator. So this fictitious term just becomes minus omega RF times IZ. So I have to work out what these individual terms are. So the first one is easy. A rotation around the z-axis around IZ doesn't do anything to IZ. They commute. I just get this. And I've taken the omega R minus omega RF IZ and lumped it in with the other IZ terms. So here I have to know how Ix transforms around the z-axis, how Iy transforms around the z-axis. And in my right-handed coordinate system, Ix is going to rotate towards the plus IZ axis, and Iy is going to rotate towards the minus Ix axis with sine and cosine projections. So here Ix becomes Ix cosine omega Rf times t plus Iy sine omega Rf times t. Iy is Iy cosine omega Rft, and it rotates towards minus Ix. This looks like rotation of a vector. I'm rotating the matrices. So you have to believe me for a moment that these rotation of the matrices behave like rotation of the vectors. And again, we'll justify this later on. But if I believe these results, I plug them in and I find, first of all, the Hamiltonian is independent of time. The amplitude here, omega 1, is the amplitude of the pulse. And now the phase of the pulse of the rotating frame becomes the phase of the RF in the laboratory frame. The phase of the RF in the laboratory frame, of course, is whether when I turn on the pulse, does it look like a cosine wave or a sine wave? But in the rotating frame, that turns into what I think of as the pulse phase relative to the X and Y axis. And that always kind of strikes me as sort of astonishing. That the phase of this field turns into what appears to be a fixed rotation axis in the rotating frame. And here, this bit, omega naught 1 minus sigma, what we think of as the resonance frequency of some spin, then becomes in the rotating frame omega, the difference between the true frequency and wherever we put the carrier. We call that omega, or the resonance offset. And if we put the carrier right on top of a peak, on resonance with the peak, omega is going to be 0. But in general, the proton spectrum spans a few kilohertz. And if we put the carrier in the middle, some spins are going to have a positive offset and some spins are going to have a negative offset. But this term is going to be on the order of kilohertz, not megahertz anymore, because we jumped into the rotating frame. Yep.
So in the rotating frame, if the magnetization is evolving under the offset, does the phase still remain the same or does it change with time?
So here, we're just asking about the Hamiltonian. And in the rotating frame, the phase, if you like, phi here of the Hamiltonian was fixed by the phase of the RF pulse, of the RF field when we started the pulse. Now, the phase of magnetization, that's going to depend on evolution of the density operator under this Hamiltonian. So for that, we have to solve now the Liouville von Neumann. But we found the transformation that rendered the Hamiltonian independent of time, which was our goal. Now, this equation here, this equation here was already a simplification. Remember, back in the block equations, we had a linearly polarized RF field that we separated into two counter-rotating circularly polarized fields. And we threw away the one that was rotating in the wrong direction. So here I've already done that. This is a circularly polarized Hamiltonian. And perhaps not surprisingly, the RF field is circularly polarized, rotating with the frequency omega RF. Our transform frame also needs to rotate with the frequency omega RF to make that look stationary. And of course, if we rotated the wrong direction, we're going to be rotating, we're going to see a Hamiltonian rotating at 1 kilohertz if it was a 500 megahertz NMR spectrometer. So we pick out which one is the right one. The wrong field does have a small effect. It's there. It causes something called a Bloch-Seigert shift. It shifts the frequencies a little bit, but generally speaking, we don't care about it. That's there, but it's small and affects everything, so we don't worry about it. Yeah.
Can you explain again what you meant, what the Bloch-Seigert shift is?
Pardon?
What is the Bloch-Seigert shift?
It's the effect of the fact that there is this other field.
Off resonance.
The off
RF
resonance
that's
field.
off resonance.
And
So
so here,
Ah,
that field has an effect that scales on the, I think, on the order of the reciprocal square of the frequency. So if we're at 500 megahertz and there's this 1 gigahertz field going in the wrong direction, it has a very small effect. But it'll turn out in other cases when we're generating counter-rotating fields with shape pulses, for example, then these fields aren't so small and there is a measurable Bloch-Seigert shift that sometimes you try to compensate for.
So
The counter-rotating fields do have an effect. When we're talking about the rotating frame transformation and it's hundreds of megahertz, the effects are very small.
that's just because of how we generate.
Yeah, because we generate the RF, well, in the solution probe, you're generating what you hope is a linearly polarized field with a Helmholtz coil. So not such a great field, but more or less linearly polar. And that's simply because generating a circularly polarized field is just technically difficult. And also would make it hard to have multiple coils. For us, different from you, in solids, we tend to have a pair of coils that are orthogonal to each other. One set for doing, say, hydrogen and the other set for doing nitrogen and deuterium. And because they're orthogonal from each other, they're a little bit decoupled from each other, which is good. If we were trying to generate a circularly polarized field, we would have to have orthogonal coils for both the hydrogen and another set of orthogonal coils for nitrogen and carbon, and just, can't do it. So a little different than solution where, or in solid state, we have these solenoid.
we have two coils in some of the coils, but I was just gonna say, a lot of times it comes up when you have a nucleus with a broad bandwidth and you want to do a selective pulse on one end of the spectrum and you're detecting on the other, and then it's a big effect. But it does come up when you have two nuclei that are close to each other, like the case for fluorine and protons. And people try to make use of it. Like calibrate a field, or you have to correct for it, but it's small. We don't usually talk about this, like if we're proton decoupling our fluorine, we don't usually talk about it, but small.
Are we doing time? So these next few slides go through and try to justify that these rotations of the spin operators look like rotations. And it's a bunch of algebra. And I think right now, we'll leave it and come back to it. The end result of this is actually, I think there's a cleverer way of doing it than it's done in the notes. So really give me a day to see if the cleverer way works. The end result is that we come to the conclusion that these three spin operators look like they rotate just like the Cartesian vectors do, except they're not in Cartesian space. They're in the space where the axes are labeled with the operators. And the rotations are caused by these sandwiches. R operator, R minus one. The spin operators are 2 by 2 matrices. So these rotation operators are 2 by 2 matrices as shown here. So this is different from Cartesian space. If we rotate in Cartesian space a vector along X, it's a 3 by 3 rotation matrix because it's a real vector in real space. So there's a certain kind of isomorphism between a real space and the space where we're rotating IX, IY, IZ. But mathematically, the details of the mathematics are a little different because one's a vector and the other is a matrix. One is a 3 by 1 vector and the other is a 2 by 2 matrix. Of course, as I said, as much as possible, we're going to work with the symbols, not so much with the matrices that are behind the symbols. But anytime we're stuck, if we don't know what to do, we can always replace all the symbols with matrices and work things out by normal matrix algebra to figure out how we go forward. We're going to assume a right-handed coordinate system. So in our coordinate system, if your thumb is on Z and your fingers are on X, you should curve towards the plus Y axis. Otherwise, you have a left-handed coordinate system and you'll get everything backwards from how I'm doing things. The equations are shown here for the different matrices and their inverses. But of course, I usually just remember that the originating operator is always going to be modulated by the cosine of some angle. The destination operator is going to be modified by the sine of some angle. And then whether it's the plus x-axis, the minus x-axis, I can always just figure that out by putting my thumb along the rotation axis and my fingers on the starting operator, and then figure out where the destination operator is. Just like we did for figuring out in the block equations what an off-resonance rotation looks like, where we don't have a rotation around a single Cartesian axis. We have the same formalism here. I can represent a rotation around some arbitrary axis by, first of all, rotate around Z to get rid of the phase, come back to the IX axis, then rotate around the IY axis to put the effective Hamiltonian on the Z axis, rotate around Z by the rotation angle, and then undo the first two rotations. So this is completely analogous to what we did for the block equations for the magnetization. Of course, we could say if I knew the rotation axis, I could just rotate around that axis, and if n is the rotation axis and I is my operator, and this is the operation. It's not so convenient. So here, this is just kind of here for reference. And then this will come up later on if we have a well-behaved function. I'll leave that unspecified, of some operator A, and we transform, then that's the same as the function operating on the transformed operator. I'll leave aside for the time being what a well-behaved function is. But this is a very useful identity many times. So now we have the Hamiltonian, at least for the chemical shift. We have the transformation into the rotating frame where the Hamiltonian is independent of time. In that frame, it looks like we're just doing rotations in this funny space defined by Ix, Iy, Iz. That's called the Hilbert space, the differentiated from Cartesian space. All we really need to know is what's our representation of the Boltzmann equilibrium, and what's the operator for observation of the NMR spectrum at the end of the day. So the equilibrium density operator has this form, e to the minus I h, where h is going to be, for us, h naught, the Hamiltonian where we just have the static field, where we haven't turned on any fields, normalized by the trace of that operator, where trace, remember, is the sum of the diagonal of the matrix representation. So if we work with alpha and beta, or more generally, whatever the spin states are, or an arbitrary spin that might have more than two states, then in the eigenbase, we just have each element of the equilibrium density operator is given by this expression. And for example, for us with spin 1/2, M and N are either alpha or beta, and H is just going to depend on Iz, right? Because if we look back at the Hamiltonian, if we don't have a B1 field, if we're just waiting for Boltzmann equilibrium, here we just have the Larmor frequency times Iz. When I come to this equation, this is the exponential of Iz. It's just a bunch of Iz's multiplied together in Taylor series. Iz acting on alpha gives back 1/2 alpha. Iz acting on beta gives back minus 1/2 beta. We can expand this in Taylor series, do everything term by term, and we end up finding that this part is just the energy of that particular spin state, alpha or beta, divided by KT, and then a Kronecker delta. So if we're not talking about alpha alpha, we get 0. Not talking about alpha alpha or alpha beta. So the density operator is diagonal at equilibrium. And the diagonal elements, these are just the Boltzmann spin population. Those are just what you expect from the Boltzmann equilibrium. So unsurprisingly, the density operator at Boltzmann equilibrium has no transverse elements. So we can't sell power to the power company. And the diagonal elements are just the Boltzmann population. A very simple result. And again, since this is these exponentials are very small, very close to unity because the arguments are very small at our temperatures and with our energies. This can be expanded to first order in Taylor series. So here's what we get. There's the part that says the populations are almost equally populated, and then the deviations from equal population. The part that's proportional to the identity operator doesn't have any effects in NMR. So usually when we talk about the density operator, we really mean the reduced density operator, the part that deviates from equal population. It would be better if I used different symbols. It would be better if up to here, when I'm talking about the equilibrium density operator, I call this something else like rho, is sometimes used in the literature. And then I said we would call sigma just this part, the part that's deviation from equilibrium. But I didn't. So you should know that from now on, when I talk about sigma, I mean the reduced density operator, the deviation from equally populated states. But you should pay attention. Sometimes in the literature, people are more precise, and you might need to pay attention to whether they're talking about the full density operator or reduced density operator. The good thing here is you can see that a reduced density operator is just proportional to IZ. With some proportionality constants, H bar omega, remember, is the energy. AT is the Boltzmann constant times temperature, and is the number of spins in the sample. We already said we're going to work in units of H bar equal to 1. Most of the time, NKT won't be written. And the omega won't be written if I'm talking about a homonuclear spin system, or if it's clear what I mean by different spins. I don't want to get mixed up. The density operator, for example, if I have both nitrogens and hydrogens, the components in the density operator are going to be scaled by omega, which differs by a factor of 10. But in lots of calculations, that's unimportant to me. So you may see that we say the density operator is proportional to IZ and just go on from there. Forget about all these constants. Or in other cases, the omegas may be included to help us keep track of which is hydrogen and which is nitrogen through a calculation. But if you want real numbers, eventually you're going to have to go back by unit analysis and put in the H bars, the Ks, the Ts, and the numbers of spins. And lots of time, if we just want to know where the peaks are in the spectra, this is enough. You're just saying IZ. The amplitude of the peaks are going to depend on all these other factors. Well, that's good. So now we have the equilibrium density operator. We start with something that depends on the Z components. And that's nice because if we turn on an X pulse, we know how IZ rotates. So we can say we have equilibrium magnetization on the Z-axis. if I turn on a 90-degree pulse along X, that magnetization is going to end up on minus IY after the pulse. And now if at this point I turn on the receiver, I just have to know what does the detection operator look like, because then I have my recipe for detection of something that says I take the trace of the density operator times the operator associated with my detected NMR spectrum. The IY magnetization that I generate after the pulse, of course, when I turn the pulse off, it's going to process around the z-axis. It's going to be continually turning into a minus IY to plus IX, depending on resonance offset in the rotating frame. So by convention, we've decided to detect M plus. We could have decided to detect M minus, but somewhere in the dawn of time, somebody decided we should detect M plus. So to find out what M plus is, we have to take the trace of M plus with our density operator. M plus, going back towards the beginning, depends on the number of spins that we have. Gamma, H bar. And then F plus here is defined as the sum of I plus for the different types of spins that we have. Because we may be detecting methyls and amides. We have to keep track of this separately. Generally, the receiver is tuned to only one nucleus. Modern consoles, that's not true. You can detect two different nuclei at once, but I don't think anyone's thought up a really useful experiment yet for that. So this sum would usually be restricted to the different types of a given nucleus. So methyls and amides and aromatic hydrogens, for example. Although in principle, it could be hydrogens and nitrogens or carbons on a modern machine. So at some level, we're done. We can put in more complicated Hamiltonians, which is what we'll start to do next time. But the formalism is basically going to be the same. So here now is the one pulse experiment. We need the trace of the detection operator with sigma as a function of time during acquisition. During acquisition, sigma evolves by rotating around the z-axis, the IZ axis, with a frequency given by omega in the rotating frame. And the initial density operator at the start of acquisition is the density operator that we got after the pulse. If we applied a 90-degree pulse around the x-axis, the density operator after the pulse is the result of a 90-degree rotation around the x-axis applied to Boltzmann equilibrium. So here's Boltzmann equilibrium. The rotation is the x rotation acting on the equilibrium, and then the inverse rotation. Rotation around z is that operator, and here's the inverse of that operator. Always these sandwiches. U something U minus 1. And then here's the detection operator. So the equilibrium density operator is IZ times a bunch of constants so that I can bring outside all of these calculations. And I know that a rotation of IZ around X by 90 degrees generates minus IY. So I've made that substitution. A rotation around Z of IY goes towards minus Ix with a sine modulation and stays on Iy with a cosine modulation. That okay so far? And then I just need to know what's the trace of I plus with Ix and the trace of I plus with Iy. So I can do this multiple ways. Here, I've written I plus as Ix plus I times Iy. And then I just multiply everything out. And then if I go back to my definition of Ix was a half, 0, 1, 1, 0. So I have to multiply those two matrices together and add up the diagonal elements. And I find out that I get 1 for that. Here, Ix, Iy, I multiply the two matrices together, sum the diagonal elements, and I get 0. We would say Ix and Iy are orthogonal to each other. Here I have Iy times Ix. I multiply the two matrices together, and I also sum the diagonal elements, and I get 0. Here, Iy times Iy, and sum the diagonal, I get 1. So I end up that my signal is all these constants times sine of the offset times minus I cosine of the offset. And then I recognize that this can be written as a complex exponential e to the I omega t. And then there's a phase factor that comes from getting this to work out with Euler's law. The phase factor of minus I over 2, that simply tells me that I started on the minus y-axis, not on the x-axis. And of course, I would trivially correct that at the end of the day on the spectrometer by applying the zero order phase shift. So factors of I for NMR spectroscopists turn into 90-degree phase shifts. Because Euler's law says e to the I theta is cosine theta plus I sine theta. So if theta is pi over 2, e to the I pi over 2 is just equal to I. So if you've wondered your whole life what I really means, what does the square root of 1 really mean? It means a 90-degree phase shift in the complex plane. And for us, that's trivial because then we just do a 90 phase rotation. So this recipe is just what we have to apply over and over again in NMR. Now we're going to make the Hamiltonian a little more complicated. But that means these funny spaces that we're working in, where instead of Cartesian axes, we have operator axes like Ix, Iy, Iz, are just going to get more complicated. But everything is still going to look like a rotation in some kind of space. And this recipe is just going to get applied over and over again. So the hard work is done, actually. This was the hard mathematical work. And we're going to increasingly try to work with the symbols and the matrices as little as possible. So this is a good point to stop, because the next thing we have to do is ask about what other terms can there be in the Hamiltonian. And in solution, that will be primarily the J coupling. So then we have to ask, what is the operator representation of the J coupling? Fortunately, the J coupling is independent of time. So we're not gonna have to worry about any more frame transformations, which is nice. But we do have to know what its operator representation is. And then if we have two coupled spins, what do their wave functions look like? And once we know that, we're basically done with solution NMR theory until we talk about relaxation. Because 3 spins are just going to make all the matrices bigger, but not introduce anything new. A really key part of NMR, at least NMR as I know it, is that the terms in the Hamiltonian are never more than pairwise interactions. Well, the Hamiltonian can have interactions in it between, say, 2 hydrogens or a hydrogen and a nitrogen, but there aren't terms in the Hamiltonian that depend simultaneously on 2 hydrogens and a nitrogen. If we have interactions between 2 hydrogens and a nitrogen, they're always going to appear as the interaction of hydrogen 1 with hydrogen 2, and then separately the interaction of hydrogen 2 with the nitrogen, or some permutation. If you like, there aren't quote unquote 3-body interaction, at least in the kind of NMR that we'll be doing. And that is just a really tremendous simplification for our analysis. And it really means once we understand how 2 spins interact, we're basically done. After that, it's a lot of crank turning. So at this point, we're going to take a few minute break, and then people who want to stay and work on the problems will work on the problems mostly on the board, I think.
I have,
Or do you have a presentation?
no, I can scratch on my laptop.
Or we'll switch to the Zoom operator and scratch on the laptop. To start talking about the problems, and we'll record that as well. It'll be part of the recording, so you can look at it if you need to go now. And we'll finish by 3:30 because it turns out there's another group coming in. So while we figure out the switch of the Zoom, we'll take a 5-minute break. Everybody can stretch their legs. And I don't think we've ever had a TA who wanted actually to do the problems for us.
No, this is our
This is
experiment
great.
this year. I'm very happy about it.
Okay, so you need this plug, you need power.
I don't think so. Is there a power plug?
Does this plug is on the floor?
No.
Okay.
But yet, it's a power cord separate.
So the Zoom was in an email from Whitney.
With
For me, a 5-minute break and get some coffee.
Recording in progress.
Is that so I probably am audible. Here. To project.
Displays must not be mirrored.
Oh,
Yeah. I'm like, if I thought that.
They're displays.
Do you have any? That we should.
One has anything to do with Zoom.
Probably
Study. Is this Windows? There should be. There should be a thing where you- No, it has to do, it has nothing to do with this.
oh, okay.
Just has to do with the fact that it doesn't know there are two displays, it doesn't know you want. Yeah. We have any Windows users here? I'm just wondering how you get, where you get the display that shows where your two displays are. See, it is.
I don't have multiple displays.
Right, but, I mean, on the Mac, there's a thing called, under the settings, something called display. It shows.
One on display settings. In Mac, there is one in display settings. Yeah.
How we.
Yeah.
Here's the output of the screen.
Yes. Oh, okay.
I know nothing about Windows.
Okay, I used to have it,
That's it.
and I dropped my computer and it broke on the spot, and then I got
Okay.
the Apple, like the hardware, it's different.
Yeah.
That's all I know.
Magic hands.
So you have to mute your speaker. I'm just because everyone will come out from somewhere else. So this one we just like sound.
But I think it's actually then my big speaker has now changed to.
Yeah,
the
we don't
system.
want. Yeah, we don't want to do that. Okay. Then there'll be echo.
Yeah. I wonder if I can be heard online.
Yes, you should be. Okay. The microphone's right on the lectern in front of you.
This, wait,
Yeah. They should hear you.
I'm just going to assume that they can.
Ask.
I have.
You might want to speak up a little bit.
Can people hear me? Nobody's unmuted.
Nobody.
Yes, we can hear you fine.
Okay.
Yeah, I can hear you loud and clear.
So doing the problems is important. You can listen to me talk and nod, but if you can't do the problems, then you're not learning as much as you can. And so I encourage you to do the problems. I do them every year. I love doing problems. It saves me from doing my real work.
Let's go that opportunity for you.
And then you should probably introduce yourself and say a little bit about your work before you start.
Yes, thank you. So my name is Anish. I am a third year PhD student in Hans group at Columbia, and I'm doing membrane protein solid state NMR and group structure and dynamics. And yes, I'm going to be your TA of sort for this semester for this class. We have a little less than an hour, so we definitely can't go over the entire problem set. This session is intended so we can go over like the most challenging or sort of the places where you're most likely to get stuck when working through the problem set, so you can then review that at home and work through the whole thing by yourself. I just realized I'm related to codes. You have no time.
And while that's happening, I posted in the Dropbox a document called Mathematical Review for NMR Spectroscopy. So if you need to review things like matrix multiplication, etc., that document is there. It also has some problems and the keys embedded after the problem.
Coffee. Okay, so the first thing I'm going to talk about is just generally like a review discussion on 90-degree pulses, and something that we as NMR spectroscopists do on a regular basis. We've already gone through some of that in over the course of this lecture and the last week as well. But just to start with saying that, okay, great. So this is working at least. Technical point of view. I have an on resonance RF field along X. So an X is RF field with a nutation frequency, or what are called today the Rabi frequency, in radians per second as omega 1. My first question I'm going to throw at you is, what's the equation that will give me the duration of the 90-degree pulse corresponds to this nutation frequency? Say I want to find pulse duration for 90-degree. I have the nutation frequency radians per second omega 1, then anybody online can also speak up at any time.
2 divided by 1.
Right. So this is for an on resonance 90-degree pulse for a power omega 1 in radians per second. I get Rabi frequency. I get pi over 2. So typically, we talk about offsets and RF strengths in kilohertz and not radians per second, which is what you do when you get on the instrument and you're trying to calibrate pulses in relation to lengths and so on. And so the easiest thing to do is to divide throughout this equation by 2 pi. That gives us as 1/4. Omega 1 over 2 pi, or mu 1 in hertz. This becomes a mu 1 hertz times the pulse length in 90-degree pulse length is equal to 1 over 4. At least for solid state spectroscopy, it's not unusual to have pulses as short as 2.5 microseconds. If you're if you're like me and you like uh, a certain memorization of basic numbers that you can then use in the spectrometer, a 2.5 microsecond pulse is 100 kilohertz in nutation frequency. And you can then use this relation to scale up or down or to higher or lower pulse. This problem set focuses very in great detail on the effects of on and off resonance pulses and what happens when you're on resonance with something and off resonance, the different set of spins. At least for us, as solid state spectroscopists, this is most prominent for C13. C13 is the nucleus that we engage with most regularly. This is also true for C13 in solution because the chemical shift range of C13 does not change very much. So when we think of the C13 span, chemical shift, for a protein or for a typical biological macromolecule, you have, say, the CO carbonyl range around 175, followed by a fairly broad aromatic range. You go from 160 to 110. And then an aliphatic range that this is of course not drawn to scale. Very poor diagram, but 75 up to 50. Where I'm going to put all of the aliphatics. Of course, leucine is going to follow that. On a typical ultra high field or even a high field magnet that we use for biological NMR, like let's say you're on the 800 megahertz and the carbon armor frequency is around 200 megahertz. Direct ratio isn't exactly a fourth, but let's say, for C13, the omega naught is 2 pi, 200 megahertz. And if you wanted to excite all of carbon at the same time, then you would probably place your carrier smack in the middle of this. Like, I want to excite the aliphatic carbons, the aromatic carbons, and the carbonyl carbon all at the same time. And so you pick a carrier which is roughly in the middle, and usually, as far as I know, on the experiment that I've done, the carrier lands at around 100 ppm. So I'm on resonance with 100 ppm or 100 to 110. I don't know if art has, people use other carriers for broadband carbon excitation. Yeah. I usually see that.
A lot of times, people are just addressing one band or the other because
Yeah.
they can't. Yeah.
Yeah. This is the problem I'm trying to illustrate with
Yeah.
this discussion.
Yeah, go ahead.
Okay. If I'm on resonance at 100 ppm, then my carbonyl is off resonance from that pulse by around 75 ppm, 75 to 80. Let's assume for the carbonyl, the offset is 80 ppm. You've got a carboxylate group, the downfield carbonyl at 180. So the offset is 80 ppm. What does the offset in hertz if the offset in ppm is 80? Sorry? So I'm asking about capital omega, the offset for the carbon is 80 ppm, then what's the offset in hertz? I'm on 900 megahertz. Carbon armor frequency is 200 megahertz. Your offset is 80 ppm. The offset in hertz becomes anybody online? Because remember, we need to compare the offset with the typical nutation frequency, and nutation frequency is in radians per second or in hertz. It's based on pulse length. So, yes. 16
Thanks.
missing an order of magnitude, do you think? 16. So, ppm is a unitless placeholder. It's 10 to the minus 6. Your 10 to the minus 6 times 80 relative to arbitrary reference frequency. So then if you're 80 ppm of carrier and you're on 200 megahertz, so I get 80 times 10 to the minus 6, which is a placeholder for 80 ppm, and 200 times 10 to the 6 hertz. I just put that in and I get 16 kilohertz as the offset at the far end of the carbonyl region, in the middle of carbon. And you'll get a similar number for, say, the methyl carbons of alanine and uracil and so on, which will also be around 16 offset. So in order to excite carbon broadband and have as minimal an offset as possible, so let's talk about what the effect of this is going to be. Well, before that, my point is you need a pulse of nutation frequency of omega 1 such that its magnitude or amplitude is much greater than offset in order to. But if you can't do that, and if your capital omega over omega 1 is much less than 1, then you're on resonance practically. But if that condition is not true, then you have off resonance effect, which will give you inefficient excitation and it will give you a phase error. So I've picked out two problems which talk about this effect in a very interesting fashion. One one is problem 4, which says prove that nulls in the excitation profiles of on resonance 90 and 180 pulses are obtained for resonance offsets of capital omega equals 15 times omega 1. Capital omega equals 3 times omega 1. The nulls occur when they're off resonance magnetization undergoes a rotation by a multiple of 2 pi.
What do you mean by nulls here?
So, on resonance 90 pulse, you would expect certain amplitude. A null be you applied the pulse and you didn't see any magnetization at that offset. Similarly, for 180, you expect to do an inversion, like you go from plus Z to minus Z. So instead of doing a full inversion, you actually did nothing. That's what it really is. It's as though you did nothing to the pulse. And the hint tells you that that will happen when the rotation is multiple of 2 pi, which basically means that the magnetization did a full circle or did a certain number of full circles.
So just to confirm what the question is asking, we apply 90-degree on resonance pulse and yet we don't see signal.
So the magnetization went back to where it started. Yes.
At some resonance offset.
At some resonance offset.
On resonance, you're going to see full signal because you did a 90 degree. But somewhere off resonance, you're going to get no signal.
Does that make sense? Like it's kind of like you want to excite. You go back to the carbon sort of scale that I was showing you. You want to excite something at say. You apply a 90-degree pulse on say an aliphatic carbon at say 60 ppm, and you apply so your offset or your carrier frequency is 60 ppm, and you apply the 90-degree pulse, and you saw zero signal in the carbonyl region. Is this making sense? Obviously, on resonance, where your carrier is, you will see a lot of signal. So if my carrier is somewhere here, then in the aliphatic region, I will have signal. But the question is asking, at a certain offset, you will see no signal. And the question is asking you to prove that will happen for an offset that is 15 times the nutation frequency, or Rabi frequency. And then for the 180-degree pulse, it will happen for 3 times the Rabi frequency.
I think a square root got lost.
Oh, that's right. Thanks, Sam. I didn't forget about that. Somehow, when I copied the problem into OneNote, it disappeared. Okay, so given an arbitrary offset along Z and a nutation frequency or Rabi frequency of omega 1 along X, so that's what's happening, right? In the rotating frame, I have an offset capital omega along Z, and I have a Rabi frequency omega 1 along X. Then what is the effective magnetic field experienced by the magnetization? By that bit, which has an offset capital omega. Right? So it's the magnitude of this vector sum. And you're applying a pulse which is a 90-degree pulse, which, as we already said, is this. Right? So what this means is that while the target on resonance magnetization does a perfect 90 rotation in this time period, the magnetization that is offset is experiencing this effective field which is at a certain angle relative to X. So it will do a perfect 360 rotation around this, or multiple of 360 if you have really large. And it will come back to Z at the end of that. How do I set that up as an equation? Relating the pulse length, the effective field, to the fact that a full rotation has happened. In other words, if you have omega effective as the field, it's the effective field, and you have the pulse length, how do you calculate the angle through which the magnetization will rotate? Right? Right? Makes sense? For on resonance, omega effective is exactly equal to small omega 1, so that is exactly 90. For off resonance, this is so for if I want a null signal, this flip angle should be what? As the question hint tells you, it should be a multiple of 2 pi. Right? So I'm just going to say the lowest offset for which you will achieve this is simply 2 pi. So that gives me this. Doing it right? Then if you square both sides, you end up with makes sense. So this is, I guess, fairly straightforward way if you wanted to achieve selective excitation and you had the offsets lining up in this fashion. You could stay on resonance and line up the omega 1 field such that it is the offset divided by the square root of. You can apply the same logic to the 180-degree pulse. The only difference there is that there your pulse length is not going to have this, obviously. Does that make sense? Pulse length is twice that, so it's pi over 2 omega 1. That will then give you square root of 3 omega. It is also a way of potentially achieving selective inversion. The offsets, again, can be, if the mutation frequency can be set up, as that multiple of the offsets. We should just work that out as well. So for 180-degree pulse, pi over omega 1 is the duration of that 180-degree pulse. And in that duration, the magnetization which has an offset perform the full 360 rotation. Does this make sense? I don't know if this trick can be used successfully to selectively excite carbon.
Well, we use this all the time in solution.
Oh, okay.
So it's very common if you're applying pulses on the C alphas or the C betas, to use this then to get a null at the carbonyls. And it obviously is perfect only at one offset, but the carbonyl spectral width is pretty narrow.
Yeah.
So it works quite well.
Or like old school solvent separation.
Yeah. If we have to go the other direction, excite carbonyls and you want a null at the aliphatic, it doesn't work as well because the range is larger. So one might then switch to more shift or band selective pulses that are more complicated. But it's quite common. If you're pulsing a 90-degree pulse or 180 on the aliphatic, this is used all the time to get a null carbonyl.
Yeah, I like how in protein NMR we often pretend like the aromatics don't exist.
Yes.
But yeah, to a first approximation case, it's just COs and aliphatics for protein. I guess this is not true at all for nucleic acid NMR. And right there, you would have to again apply different tricks, different grouping of.
You have to ask
Yeah.
him when he
Yeah.
comes. And many of the Bruker pulse sequences now just have this calculation embedded in the header
Oh,
of the pulse sequence. Assuming, if you're putting the, for C alphas, if you're putting the carrier at 55 parts per million, and the carbonyls are at 175, it just does the calculation. You don't even notice it.
55 and 175. 100, okay. This will probably become work better as you go higher in field. This is always the case with selective excitation. You don't want to go too low in mutation frequency that within the aliphatic range itself you have inefficiency. Okay, that was problem number 4. Kind of like
I mean, one more thing to say about that is it should drive home that the rotation angle off resonance is always larger than the on resonance rotation angle, because the hypotenuse is always longer than either leg of a right triangle. And
it would be effective and always.
for an NMR spectroscopist, an angle is almost always a frequency times a time. anytime you're thinking about angles, you're wondering what frequency am I talking about? What time?
Okay. This is the next problem I've picked up. I think we have just enough time to discuss this. This involves the calculation of rotations for an off resonance pulse. And the resonance offset is quite substantial, so a lot of approximations that we have are not going to work very well. It says the spin has a resonance offset of 10 kilohertz, omega over capital omega over 2 pi. RF pulse of duration 25 microseconds, and the nutation frequency is 10 kilohertz. So gamma B1 over 2 pi, which is mu 1. So you have an offset of 10 kilohertz, and yeah, omega 1 over 2 pi, the nutation frequency is also 10 kilohertz. Taking resonance offsets into account, what is the state orientation of the magnetization after the pulse? Calculate the observed time domain NMR signal. How does the amplitude and phase compare with those obtained from ideal on resonance pulse? Same duration. Okay, so I'm just going to first discuss this part, which is what happens to an ideal on resonance pulse in the same duration and amplitude. The question already tells you that the duration for the 90-degree pulse is 25 microseconds. And I am going to assume this is an X-phase pulse. Here is an X-phase pulse. Nutation frequency 10 kilohertz, and I have magnetization on Z. Assume you are on resonance. Then where do you end up at the end of the pulse? I'm just going to use right-handed rotations.
So negative y?
Minus y, right? So you end up minus y, and your amplitude is 1. 1 in the sense that the entire magnetization, bulk magnetization has been rotated to the y plane, and you're on minus y. Relative to that, so relative to 1 being the amplitude for a perfect 90-degree pulse, and relative to minus y being the phase for a perfect 90-degree pulse, what is the amplitude and phase for a magnetization that has an offset of 10 kilohertz? This is what this question is asking. So, all right. The first thing we need to do is find out what the effective field is and how it's aligned in this coordinate system that I've drawn. So I've drawn X showing the omega 1 field, Z showing the bulk magnetization. And if I were to just look at it from the direction of Y, then again I have anybody who remembers from trigonometry what the angle will turn out to be.
45 degrees.
45 degrees, right? So pi over 4 is the angle that the effective field will make, and its magnitude. Of course, the way I'm doing that is this is generally an angle theta. Theta is tan inverse. Over. That's right. Doesn't matter in this case because they are the same number. In this case, it will turn out to be pi over 4 or 45 degrees. And the effective field I like to hold square root 2 until the end of the calculation. things work out simpler. You can go into calculated number if you like. Okay, so we have to now think about this effective field, which is here at an angle theta, relative to both the magnetization and the Rabi frequency, or the Rabi field, I should say. You have this, or maybe I should just, and this increase. Of course, this magnetization is now going to do a circle around this, on very good at drawing this. That makes sense. So, if it were on resonance, then it would just perfectly come down to minus y. But because you have an offset, you're going to do mutation. You're going to mutate around this effective field. I find that the simplest way to do this is to think about performing rotations where the effective field is brought to the z-axis, and you can perform a rotation and then bring the effective field back to where it was. That makes sense? So this is the effective field at an angle theta respect to the z-axis. I perform a rotation about y through minus theta. Then I bring this field up on z. Does that make sense? So this is rotation about y, bring the effective field on z. When I do that, then magnetization is also rotated because the magnetization goes on z when you started. So performed an Ry of minus theta operation. Then I'm going to nutate. In this case, I'm going to do it in that sense. Around z, around the effective field, magnetization. So that becomes an Rz operation through an angle alpha, where alpha again is the flip angle. That's the effective field times the pulse length.
Does it matter if the magnetization ends up in the YZ plane or the other plane when we are moving it by angle minus theta? It's like here we
You
have.
mean on like, are you talking about the sense of rotation?
Yeah. So like we have this effective omega at z. You did negative theta, right?
Yeah.
So the magnetization is just going in the YZ plane.
Well, it's no, right? Because I did a rotation about y, so it moves into the xz plane.
Oh, I see.
Right? This is just
So rotation of
trouble of doing 3D visualization of 2D.
it's
So
like
the-
backward.
It'll be going backwards into the board, towards the minus x-axis.
Yeah.
Everything you do to omega has to be done to m.
Right. So now this magnetization has rotated through an angle alpha. So I have now this is the effective field. It has done some rotation. Now I need to bring the effective field back to where it was so that I can come back to lab frame. So this comes here, and this magnetization lands up in some weird location, which is not minus point, which is where the on resonance magnetization would end up. this becomes an Ry into theta. So basically what I did was 3 rotations in succession. And that is 3 successive matrix multiplications. Which will give you the magnetization at the start of acquisition. And because we have 45 degrees, we have some symmetries in this with this 45, the tan of pi over because of the simplicity of trigonometric properties. So these are the formulae for matrices. This is the rotation about y through an angle beta, and this is the rotation about z through an angle beta. Theta in this case is just 45 degrees, right? That's just the angle that the effective field makes with respect to z. And alpha is omega effective times the time duration of the pulse. So the omega effective we said was 10 times the square root of 2 in kilohertz. The duration of the pulse is 25 microseconds. So that would be, you have to multiply those two and then give it an additional factor of 2 pi so you can get the angle alpha through which the magnetization has to be nutated. Some useful things that you can use are that cosine and sine of 45 degrees are both 1 over square root of 2. So that gives you, if I get my sine right, so what I'm going to do is I'm going to do this step by step. And if we think of m0, we start on z. So how does that unit vector look in terms of its 3 components?
To start at z.
Yeah.
0, 1.
Right. This is where I'm going to start rotating. I'm going to start rotating with this operation. So I'm doing Ry minus 45 from 0, 0, 1. That's going to look. I just plugged in the values of cosine and sine of 45 into this and I end up with, this is the first step of that rotation. That gives you right. This problem is just cranking through the matrix one after another. Yes.
Do you think it's useful to have this rotation matrix in memory?
Oh.
No.
So, I mean, I would say that I know that I start on Z. If I'm doing a minus Y rotation, I know I'm gonna rotate back towards the minus X axis. And the start is always going to be a cosine. So the Z component at the end is going to be cosine in the Z position. And the X position is going to be minus of a sine. So I could write that down without thinking about the matrices themselves.
That's what part of this value. You just pick up the cos component in Z and the minus sine component X, which is what full 3 by 3 is also given.
I need the matrices, I have to look them up, I can't remember anything, including my own name.
Then the next step, so I did RY of minus 45 on and not. The next step is rotation through Z. That one is we're going to hold alpha here because it doesn't necessarily simplify anything.
So here, for example, before multiplying things out, I know rotating around Z doesn't affect Z. So that third component had better stay the same. And then I'm on minus X. Minus X is going to rotate towards
Minus
Minus one.
minus Y. So I better end up with what started as X, that first bit, the better come back is minus 1/√2 cosine alpha. And then the Y component had better come back minus 1/√2 sine alpha. Just from thinking about the right-handed rotation without actually multiplying the matrices together. And of course, I can always multiply the matrices to prove it. For myself, working day to day, I think more about just visualizing the axes.
That was the second rotation. Then we have to do one last. We had RY plus 45 at the end. Now I'm not so sure you could still work without doing the matrix multiplication.
So you can do it bit by bit.
Yeah.
You can first ask, starting at the top, what happens to something on X if you rotate by Y?
Yeah.
So the X is in negative cosine and if you rotate about one. And that's like again cos negative IZ cos. So IZ cos some angle sine some angle.
So if we started with minus cosine alpha√2 at the end, X part stays on X, so we have minus cosine alpha√2 cosine of 45, which is another √2.
Yeah.
And then the X part rotates to minus Z. We're going to have a minus 1/√2 multiplied by the minus cosine alpha 1/√2. We're going to end up with a plus cosine alpha
Over 2
over 2
in Z.
contribution to Z just from that component.
So you had, that's what Art is pointing out here. You'll get this, and then you get this.
You have to be very careful about the minus signs, but if
Yeah.
you're doing what I'm doing, you have to be very careful.
Yeah.
If you do the matrix multiplication, it figures out the minus signs for you. And then the middle part, right, is the rotation around Y,
Will remain unaffected.
so nothing happens. And then Z rotated around Y. Goes to which axis?
Z also plus X.
Plus X. So that 1/√2 going to stay on Z with a cosine of 45 degrees. And it's going to have a contribution to X. that goes as the sine of 45. And its magnitude started with 1 over root 2. The sines and cosines are both 1 over root 2, so we get a half left on z and a half ending up on cos f.
This is the magnetization at the end of that of resonance 90-degree pulse. Question was asking you, so we've thought about a sort of intuitive rotation based as well as walking through the matrices. So you can, this was a little fast, and you can of course always go back to the 3x3s one after another. You could multiply on the 3x3s directly if you prefer in the right order, making sure that rotations don't commute with each other. So you have to multiply them all in the right order and then go in and multiply that entire product matrix on 0, 0, 1. And you should land up in the same place. How do we make sure? So sanity checks on this calculation. The most important is that at the end of all of this, amplitude has to be conserved. So the sum of squares of these three terms has to add up to unity. This is again trigonometry. What's the trigonometry? Then if you use the relation that square of sine plus square of cosine is equal to 1, and you cancel out 2 cosine alpha from the two, by opening brackets of the two squares, you get something like 2 plus 2 cos squared alpha plus 2 sine squared alpha over 4 is 1. How do we figure out how much magnetization was left on Z? So relative, again, this brings us back to the question, relative to a perfect on resonance pulse, how much amplitude do we expect?
It's the transverse magnetization, so it's x squared plus y squared, the square root of that, and the mx squared.
Right, yes. So this term, the coefficient that we get for x squared plus the coefficient that you get for y squared, will give you the amplitude at the end of that 90-degree pulse relative to the perfect complex pulse. That will be necessarily less than 1 because the full thing adds up to 1, so that sum of those two alone will be less than 1. And then you can plug in the value for alpha and figure out that for this offset, what that amplitude is expected to be.
What's the coefficient of x here?
Right, so when you said that at the start of the experiment, you had 0, 0, 1 because magnetization was only on Z. Now you have this at the end of the 90-degree pulse, right? So the coefficient of x as in the vector component along x will be given by
The 1/2 minus cos alpha over 2.
right.
Yes.
So that's the vector component of the sum, the net magnetization, its component of projection along x. Similarly, minus sine alpha over square root 2 is the projection along y. And 1/2 plus cos alpha over 2 is projection along z, right?
Yes.
So at the end of the pulse, when you turn on the receiver, I guess I didn't say this explicitly, you turn on the receiver, as we just saw, you only see terms that will give you a trace with I plus, or M plus. Yeah. That's the operator effect. And I plus, as you saw, was Ix plus Iiy, right? Trace of, I don't remember if you were using I or M, but I'm just going to
Doesn't matter.
And if I say the density operator is, it's Ix times something plus Iy times something plus Iz times something. And these somethings are these components. I plus is again Ix plus Iiy. So when I try and take trace of this with IZ, I'll get 0. Ix IZ and Iy IZ, those traces will be equal to 0.
Okay, I see. Yeah.
And this is so what that basically tells you is the net amplitude of transverse magnetization at the end of that pulse will be the amplitude, the signal amplitude, relative to a perfect pulse.
So you'll have less than maximal signal because you've left some on Z.
You can calculate how much. And of course, here, well, okay, that was about amplitude, and again, you can use the same logic that we used here, right? So this trace of I plus sigma of t, and you can use the same logic to calculate what the phase error will be. I have run out of time, so I can't walk through that right now.
They have homework. We'll continue next time.
Yes.
Another thing, you show the answer for a second. Go back to the next one. One thing that is why this was picked to be a 45-degree angle is unlike most off resonance conditions. I mean, there is a point in which you can get all the magnetization into the transverse plane. So if you look at that result, what value of alpha
That's a very interesting question.
would give you all the magnetization into the transverse plane and none left on the z-axis? And when would the z component then go to 0?
Cos alpha equals cos pi, you get cos alpha equals. So the z component vanishes.
So you must have, if alpha is pi, you must have put all the transverse magnetization, even though you're going around the cone, it still hits at one point everything in the transverse plane. Pardon?
By example, right, so
It's going to be a different time, right, than it would be to do a 90-degree pulse. So what would the time be?
perhaps a different question is what would the offset be for a certain, because you're trying to do a 90 on beyond resonance.
Right?
So for a certain offset which would match.
No, we've already said that the offset is 10 kilohertz.
Okay.
So we're going to hit the rotation axis. We're going to
Yeah,
the
sorry.
90-degree pulse puts everything in the transverse plane after the length tau p, right? Our 90-degree pulse now. Now we see for this special offset, we can hit the transverse plane completely, but it won't be the same time. It'll happen at a different time.
Yeah.
So the time would be when alpha we decided is pi, and that's omega effective times time. Omega effective we said is √2 times omega 1. And omega 1 was equal to and the 90-degree pulse was
25 microseconds. So, relative to 25, I think you're
Um, Question is our how p, so root 2 times omega 1, how p is pi over root 2 omega 1, the omega 1's cancel, the pi's cancel, so we get that our time, our new time is how p over root 2.
Yeah.
So 40% before we hit the 90, that off resonance magnetization has already hit the transverse plane early. And then by the time our on resonance magnetization hits the transverse plane, the off resonance magnetization has moved on. But there is a time when it hits the transverse plane. It's just a curiosity. And the problem should really ask that question because it was set up. Right? If the tilt angle was less than 45 degrees, you never hit the transverse plane. So
So it's forming a cone without going through this XY.
without ever hitting the XY plane, if the tilt angle is less than 45 degrees, you can never get all the magnetization in the transverse plane. If it's greater than 45 degrees, it's greater than 45 degrees, there's 2 points where you hit the transverse plane because you sweep below the transverse plane and then come back up. 45 degrees, there's 1 point where you just touch the transverse plane. Where's the magnetization in this case when we hit the transverse plane? So if alpha is 180 degrees, the z-axis is 0. What's the sine of 180? 0, so the y-axis is 0, and the x-axis becomes 1. So in fact, you get all the magnetization exactly on x, just at the wrong time.
and at x, whereas on resonance would take you to minus y. This is going to take you to plus x. So on resonance is doing this, but off resonance you're doing that. Just come all the way down in this cone.
That's a special property of it being 45 degrees.
I mean, not of any practical use that I know of, but
So exactly at that
an
duration,
interesting,
that cone is intersecting the x-axis.
curiosity.
Okay, I think we have to get out of this.
Yeah,
People
probably.
waiting
And
outside.
if they're waiting.
I can share these notes in the
This is being recorded though, right?
Yes, yes.
Yeah.
You can also go through the recording later.
Thank you. Yeah.